In this video, we're going to talk about the development of the law of sines. But before we do, take a look at the orientation of the sample triangle that's drawn here. We see that vertex A is drawn across from the side length that's labeled A units, whatever units we're using to measure the sides in this triangle. Vertex B is across from the side length that we've labeled to be B units, and angle C, vertex C, is across from the side length that is C units long. Now the law of sines, which allows us to use some trigonometric functions to deal with non-right triangles, all hinges around the idea of drawing an altitude within this non-right triangle. So an altitude is a line segment that's drawn from a vertex perpendicular to the opposite side, and reasoning about different ways that we can represent its length. So if we let the length of this altitude be h units, and this altitude splits this side into two unknown lengths, so the whole thing is b units, but we're not quite sure how it's split up, we can start thinking about different ways to represent the value of h. Let's take a look at the right triangle here that's on the left-hand side. For this triangle, we have an acute angle here that has some measure, whatever that measurement is, so the measure of angle A, and we have the vertical leg length when we're drawn in standard position here, the vertical leg length being h units, and we have the hypotenuse length of c units here. So from what we know about trig functions, the length of this vertical leg here is going to be the length of the hypotenuse times the sine of that acute angle measure. So the length of h can be represented by c times the sine of the measure of angle A. This is based on the triangle on the left-hand side. If we look at the triangle on the right-hand side, if it helps you, you can think about redrawing this triangle in standard orientation. So I'm just going to sketch that down here real quick. All right, so we have a vertical leg length of h, an acute angle here, that's the measure of angle C. Hypotenuse length is a units long. The value of h here, for a very similar reason to the other triangle, it's going to be a, the hypotenuse length, times the sine of that acute angle measure. Now if we think about what this tells us, since both of these expressions represent the value of h, or the length of that altitude, those expressions have to be the same value. So in other words, c times the sine of the measure of angle A must be equal to A times the sine of the measure of angle C. So from here, let's divide both sides by A times C. We can also rewrite this if we look at the left-hand side here. We can think about this, we can factor the C out of the numerator and the denominator. So this is equivalent to c over c times the sine of the measure of angle A divided by the side length, A units. And we can factor A out of the numerator and denominator on the right-hand side. Now c over c, regardless of what the length of c is, when you divide it by itself, you're just going to get 1. And similarly over here, a divided by a, regardless of what the value of a is. We know it's not 0, that would be the only issue, but it can't be 0 because it represents the length of one of our sides. So in other words, we get that the sine of the measure of angle A divided by the side length A has to have the same ratio as the sine of the measure of angle C divided by the side length C. This is part of the law of sines. So this ratio of the sine of an angle measure within the triangle divided by the length of the side opposite it in the triangle is the same regardless of which of these two vertices we're looking at, regardless of whether we're looking at angle C and angle A and its side length A, or angle C and its side length C. Now let's go back and look at the same triangle again, but we've rotated it here. So we've rotated it so that vertex B is in the lower left-hand corner. So let's go ahead and draw an altitude for this orientation, vertical here. We could also label this altitude length as h. I don't want to introduce confusion because this length, this altitude is not the same as the length of the altitude in the other triangle. So I'm going to mark this as k, its length as k units. So now when we look at this triangle that's on the left-hand side, right, we've got this angle measure in here, the measure of angle B. So the length k is going to be equal to the hypotenuse length times the sine of the measure of angle B. But if we use the triangle on the right-hand side, so we use this triangle, and we have this acute angle here that has the measure of angle A. Again, if you need to redraw it in standard orientation to help you visualize the values of the trig functions here, k can be represented also by the length of the hypotenuse, which is B, times the sine of the measure of angle A. But kind of like before, what we concluded was that because these two expressions both represented the length of this particular altitude, that we must have that A times the sine of the measure of angle B must be equal to B times the sine of the measure of angle A. And now, kind of like before, we factor out the A divided by A, so we get A over A, which is 1, times sine of the measure of angle B divided by B. Well, over here, we would factor out B from the numerator and denominator. We would have B over B, which is 1, times sine of the measure of angle A divided by the side length A. So we end up getting that these two ratios are the same. But up here, we figured out that the sine of the measure of angle A over A was also the sine of the measure of angle C divided by C. So not only is this true, but it's also true that both of those are equal to the sine of the measure of angle C divided by the side length C. So it doesn't matter which pair of angle measure and side length that are across from each other in the triangle we look at, the ratio of the sine of that angle measure divided by the corresponding side length is always the same. So when we put this string of equalities together, this is the law of sines. Or at least one form of the law of sines. So one last comment before we finish this video. Note that if you have a ratio of two values, like 3 to 2, so 3/2, and if this is equal to another ratio, like say 6 divided by 4, so 3 over 2 and 6 divided by 4 have the same value. If you look at the reciprocal of each of these, so instead of 3/2 you do 2/3, and instead of 6/4 you do 4/6, that this relationship is also true. So as long as neither of the values are 0, if two ratios are equal to each other, or two fractions are equal to each other, and you invert both of them, and you look at their reciprocals, you're also going to get an equal statement. So that means that if we take this original statement of the law of sines, we could also say that the reciprocals are equivalent. So when you're using the law of sines, you can use either of these forms. It doesn't matter. Generally speaking, you're going to find it easier to use one form or the other, depending on the problem that you're given. And we'll look at a lot of examples of that in this investigation.